for inviting me to speak. So I'm going to start by apologizing for my split personality, and also there we go. I'm going to apologize for my split personality. I think when I was invited to talk, the idea was that I would give you a talk about early dark energy and the Hubble tension. But there's other things that I've been doing that I am kind of interested in, and I thought you might be interested in. And so I thought that I'd try to advertise and summarize some other work that my students and postdocs I have been doing. So it might be a slightly disjointed talk, but you know, it's a fairly small Zoom audience, and so you should feel comfortable to ask me, interrupt and ask questions. And usually I find that things get most interesting when there are questions asked. So I'll start with the Hubble trouble and early dark energy, give you like a short talk about that, and then give you another short talk about new work on the cosmic optical background. So the Hubble law describes the linear relation between the recessional velocity of a galaxy and the distance to a galaxy. H0 is the Hubble constant. It has units of inverse time, and so it describes the rate at which the universe expands. To make a long story short, there's essentially two types of measurements. There are measurements that come from the cosmic microwave background large-scale structure that give us a value for the Hubble parameter of 67.4 plus or minus smallish numbers. And then there are values that are coming from what we call local measurements, which typically involve supernovae, type 1a supernovae, which are believed to be standard candles that have been calibrated to sources in the Milky Way. And these give us a value for the Hubble constant closer to 74. So this is called the Hubble tension. It should probably be called the Hubble discrepancy. The term tension arose, on order 10 years ago, when there was a 2 sigma-ish discrepancy, but now the discrepancy is greater than the 5 sigma limit, 5 sigma level, and so we should really be calling it a discrepancy. And so that's the question. Why is it that the Hubble constant that we infer by measuring the local expansion rate differs from the Hubble constant that we infer by modeling observations of the cosmic microwave background and galaxy surveys? So I am a theorist, and to break things down to the simplest possible interpretations, either there's a problem with local measurements, or there could be a problem with CMB galaxy survey measurements, or there could be problems with both. I'm not going to talk too much about the measurements because it's not my expertise, but I do believe that both the local measurements and the CMB measurements have received as much scrutiny as any quantitative measurements in cosmology ever, and nothing obvious has been found wrong with any of them. I'm writing a review article now with Adam Rees. We're supposed to finish and submit it next week for N3AS, and one of the things that Adam points out is that this is actually the third Hubble tension. The first Hubble tension was Hubble's value for the Hubble constant. He was getting 500 kilometers per second per megaparsec, off by an order of magnitude. And that was a tension with the ages of stars. The stars in the universe seem to be older by about a factor of 10 than the age of the universe. So that was the first Hubble tension. That was resolved by the discovery that there were 2 different classes of variable stars, which is a pretty significant discovery in astrophysics. There was another Hubble tension, which was sort of similar in the 1990s. In the early 1990s, there was a value of the Hubble constant that implied, again, a universe that was younger than the stars, the oldest stars in the universe. And back in the 90s, people worried about this a lot, and that was resolved in the late 1990s with the discovery of cosmic acceleration. The existence of that cosmological constant allows for the existence of that Hubble constant allows for an older universe with the same Hubble parameter. So this is sort of a third Hubble tension, and the prior 2 Hubble tensions were resolved by very interesting new astrophysics and cosmology and physics. And Adam was involved in the earlier Hubble, the second Hubble tension measurements, and now he's involved in the third Hubble tension measurements. He believes that the evidence for a Hubble tension now, experimental, empirical evidence, is stronger than that for the cosmic acceleration in the late 1990s at the time. But he believes that we're still lacking for a simple explanation. In that case, it was the cosmological constant. We just say, let's postulate the cosmological constant. Everyone's happy with that. That's solved all the problems. As we'll see shortly, the models that we have to account for the Hubble tension are not quite as simple. So I'm going to surmise that the measurements are okay, and I'm going to investigate or discuss what it implies for new physics if this Hubble tension is real. So to do so, I need to try to explain to you how it is that the Hubble constant is inferred from the cosmic microwave background. So we live in a universe that's approximately 14 billion years old. So the cosmic microwave background surface of the last scatter is a spherical surface that we see in the early universe. The radius of that spherical surface, of that sphere, is 14 billion light years. And we are taking a snapshot of the universe when shortly after electrons and protons combined to form hydrogen atoms, after which photons were able to stream freely towards us. And so we see a snapshot of the universe, of a spherical surface in the universe 400,000 years after the Big Bang. And the radius of that sphere is 14 billion light years. This is the image that we have of that cosmic microwave background. We measure temperature contrasts of roughly 1 part in 10 to the 5 with an angular resolution on the order now of a few arc minutes. So we have the brightness of the CMB temperature, or the intensity of the CMB, and several million pixels across the sky. The way we look at this map is in Fourier space. It doesn't look like much in configuration space, but we can take a Fourier transform and then square the Fourier amplitudes and plot them as a function of the multipole moment, L, where higher L corresponds to smaller wavelength fluctuations, 0.05 degrees at the far right. Smaller L corresponds to larger wavelength fluctuations. So L equals 2 corresponds to 90 degrees. L equals 200 corresponds to roughly 1 degree. And what we see is that this power spectrum, the Fourier space picture of the cosmic microwave background, is pretty striking and fairly interesting. So it has these bumps and wiggles, and then it decays exponentially at high L. This is a log plot over here. And so we see that there are these very interesting bumps and wiggles, and those bumps and wiggles are the result of fairly simple physics in the early universe. And the simple physics is illustrated in this movie that I'm going to show you. It's playing now, and I'll pause it for a second. So what this movie shows, and you can find it on YouTube, is the evolution of an initial overdensity in the early universe. So suppose we have a perfectly smooth early universe that consists of dark matter, baryons, photons, and neutrinos. And then we add to that a direct delta function overdensity at the origin in all of the components of matter. What happens is that overdensity constitutes a high pressure region in the baryon photon fluid in the early universe. And so that sends out a shock, a spherical shock that propagates out at the speed of sound. And so that's the purple here. This is the baryon photon fluid. The dark matter is cold. It responds only to gravity, and so it stays pretty much put in the center. That's the grayish. And then there's the neutrinos, which then free stream out with time. And so they are actually going to spread out more quickly than the baryon photon fluid, as we will see. So the neutrino tail is expanding out, the baryon photon fluid is expanding out, and then approximately 400,000 years after the Big Bang, any second now. So I went a little far. So 400,000 years after the Big Bang, the baryons and photons are starting to decouple, and the photons are free streaming and giving us the picture of the cosmic microwave background that we see. But what we see is that there is this spherical shell, the spherical overdensity in the baryon photon fluid at the combination 400,000 years after the Big Bang. And the radius is simply fixed by the time between the Big Bang and the time of decoupling, which is about 400,000, of the distance that a sound wave can propagate. This is a sound wave in the baryon photon fluid, so it propagates at roughly 1 divided by the square root of 3 times the speed of light. So if we take this, so this is the Green's function for primordial density perturbations. And although the primordial density field is not a Dirac delta function over density, it's some distribution of primordial perturbations, the evolved power spectrum or 2-point correlation function, the evolved 2-point correlation function is going to have this bump that arises from this Green's function. Now, the Green's function, oops, there it is. A configuration space Green's function that has a sharp feature appears as a set of rings, appears as Fourier space ringing, as a bunch of peaks. So the power spectrum peaks that we see, these bumps and wiggles in the Fourier space CMB power spectrum, these are the Fourier transform of that spherical shell Green's function for the baryon photon fluctuation. So the angles at which these peaks occur, these acoustic peaks occur, reflect the distance the sound wave can propagate from the Big Bang to the surface of blast scatter. And the reason I point this out is that this sound horizon is the best determined parameter in the cosmic microwave background. It's determined to roughly 1 part in 10 to the 4. And so if we are going to consider any type of new physics that might affect the early universe in such a way as to solve the Hubble tension, we have to do so in such a way that preserves this sound horizon. Now, strictly speaking, the sound horizon is determined, strictly speaking, the angle subtended by the sound horizon depends not only on the sound distance, it also depends on the classical cosmological parameters. So actually, let me show you my equations. So what we actually measure is this theta sub s, the distance subtended by the sound horizon at the surface of blast scatter. So it is the physical sound horizon, the distance the sound wave propagates from the Big Bang until 400,000 years after the Big Bang, divided by the angular diameter distance, the distance to the surface of blast scatter. So R sub s depends on the baryon density in the early universe. The angular diameter distance depends on the Hubble constant today and the matter density in the universe. Now, the matter density and baryon densities are determined from the details in these bumps and wiggles in the acoustic peaks and the CMB power spectrum. So the rate at which they damp depends on some combination of the baryon density and the matter density, and the relative heights of the even and odd numbered peaks also depends on the ratio of the matter to baryon densities. So from these higher order features in the cosmic microwave background power spectrum, we can constrain omega baryon and omega matter, and then we infer the Hubble parameter by measuring the theta sub s, because we know R sub s from the baryon density, and the angular diameter distance depends on the matter density and the Hubble parameter. So let me just show you a few more equations. So this is an easy equation. These are slightly more complicated. The angular diameter distance is an integral over cosmic time normalized by the age of the universe today of the density of the universe at time t divided by the density, normalized by the density of the universe today to the 1/2 power. And here we're integrating from recombination time until today. And then this is the speed of light, and then this is the Hubble constant. The sound horizon is similar, except that the distance is the sound distance, not the light horizon. And so instead of having the speed of light, we have the speed of sound, which has a weak dependence on the baryon density. And otherwise, we have the density of the universe at time t divided, normalized by the density of the universe at time recombination. So I algebraically combine these two equations, and this gives me the equation for H naught. So I infer H naught from the cosmic microwave background by taking the ratio of this late time integral to this early time integral. So if I want to increase the Hubble parameter that is inferred from the cosmic microwave background, I can either decrease the matter density at late times, which decreases this denominator of this denominator, which then increases h naught. I can decrease the sound speed in the early universe. I won't talk about that because that turns out to be very difficult to do. Or I can increase the matter density at early times. So I increase this, by increase this rho of t, then I decrease, wait, what did I do there? Increase the matter density over here. Increase this rho, therefore I decrease this denominator, the big denominator, and then increase the Hubble parameter. So efforts to fix the Hubble or resolve the Hubble tension by decreasing the matter density at late times, subject to the constraint that the matter density today is unchanged, are called late time solutions. And as it turns out, these late time solutions do not work for two reasons. The first one is theoretical preference, and the second is empirical. So if I want to decrease the energy density in the universe between the time of recombination and today, while keeping the density of the universe constant, the density of the universe today unchanged, it requires that somehow I have some type of exotic energy density that increases with time. So you can do this by introducing some type of late time dark energy in which the co-moving energy density, in which the energy density is actually increasing with time. So if this sounds like we are creating energy out of nothing and makes you uncomfortable, that is in fact true. General relativists would say this is a violation of the null energy condition, which is general relativistic ease, for saying that you're creating energy out of the vacuum, which nobody likes. Even if, however, you are willing to consider such an theoretically unappealing solution, the model or the late time solutions don't work because of the imprint of the baryon acoustic oscillation in the galaxy distribution. So if I measure the 2-point correlation function of the galaxy distribution, there is actually a bump at about 100 h to the -1 megaparsecs that arises in the total matter density. And so we actually measure the sound horizon or see the sound horizon in the galaxy 2-point correlation function. And this depends on the Hubble parameter. And by measuring the location that we see, the angular size of this peak in the galaxy 2-point correlation function, and comparing with the sound horizon from the early universe, we infer a value of the Hubble parameter. And this also gives you a lower value of the Hubble parameter. So late time solutions cannot account for this. So that leads us to consider another possibility, which is the early time solutions, which are based on an idea called early dark energy. This comes from a paper I wrote with Tanvi Karwal, a graduate student at the time, in 2016. She's now looking for a job. So if you're looking to hire someone who knows something about early dark energy, there is your candidate. And so what we said in this paper is basically what I already told you. If the early universe expands faster, then there's less time for sound waves to propagate. That gives rise to a smaller sound horizon, and therefore you infer a larger value of the Hubble constant from the cosmic microwave background. So roughly speaking, what we're postulating is that in addition to so here's a plot of the energy density of the various constituents of matter as a function of history in the universe, with time going from right to left. So the Big Bang is off to the right, high redshift. The universe today is off to the left, redshift equals 0. In addition to the radiation, which is the blue curve, and the matter, which is the yellow curve, and the cosmological constant, which is the green curve, we hypothesize there's something else we call early dark energy that behaves like a cosmological constant at early times, but then decays faster than radiation at late times. And so what we have here on the bottom is the fractional contribution of early dark energy to the total energy density of the universe. And if that peaks shortly before recombination at redshift of about 1,000 and is about 10%, has a value of about 10%, then you can increase the sound horizon, decrease the sound horizon by about 10% and explain the Hubble tension. It turns out, though, that the so we also mentioned two possibilities for new physics, toy models for new physics. One is a scalar field with a confining potential V of phi that has a potential of 1 minus cosine phi over f to the n, where n is equal to 2 or greater. And if you have such a potential, it behaves like a cosmological constant. Oh, that should be early times. Behaves like a cosmological constant at early times. Field is frozen here. And at late times, it starts to oscillate and then decays away as scale factor of the 2n minus 2 divided by 2n plus 2. And if n is 2 or greater, then this is faster than radiation. And it's based on some string Axiverse ideas that we had presented in an earlier paper. Another possibility is something that looks like a slow roll potential for inflation, where I have a scalar field, which at early times can be displaced from its potential and is stuck and behaves like a cosmological constant, but late times rolls away, and then this residual kinetic energy density decays faster than radiation. It turns out, though, that it's easy enough to say that, but it's hard to actually get it to work in such a way that the remarkable agreement between the standard lambda CDM model and precisely measured CMB fluctuations is preserved. So in later work with Vivian Poulin and Tristan Smith, we actually developed numerical codes to allow us to evolve the early dark energy and evolve its effect on the evolution of density perturbations and their effects on the cosmic microwave background and galaxy distribution. And then we did a detailed Monte Carlo Markov chain analysis of CMB and galaxy survey data. And this is sort of the money plot from our paper. This is a 4x4 subset, actually 3x3 subset, 4x4 subset of the parameter space for the early dark energy and classical cosmological model. So the classical cosmological model is parameterized by 6 parameters: the matter density, the baryon density, the Hubble parameter, the scalar spectral index, the amplitude of scalar perturbations, and an optical depth through ionization. To that, we add 3 parameters that describe the early dark energy. One of them is the fraction, the fraction of the total energy density contributed by early dark energy at its peak. The redshift or scale factor at which it becomes dynamical. So that is supposed to be somewhere between 10 to the minus 4 and 10 to the minus 3, roughly speaking. And the Hubble parameter and the dark matter density over here. Oh, I forgot to mention the third early dark energy parameter is an initial value for the scalar field. So this is a 4x4 subset of the 9x9, the 9-dimensional parameter space. And I want you to first look at this tiny little yellow ellipse over here. This is what happens in the standard cosmological model. So here we reproduced the standard result that the CMB gives you a value of the Hubble constant around 68 in the standard cosmological model. And then these are 3 different early dark energy models parameterized, where the N is the power law index over here. And what you see is that for n equals 2, 3, and infinity, the likelihood contours open up to larger values of the Hubble parameter that overlap with the gray region, which is the allowed region from the supernova measurements. And so you see that by adding early dark energy, we are able to accommodate a larger value of the Hubble constant. What's more important, but not shown in this plot, is the value of chi-squared. So not only do we open up the likelihood contours, but you have to evaluate the reduced chi-squared in regions of these purple regions that overlap with the gray regions. And what we find is that there are indeed values of the, indeed parameter values in which the Hubble constant is consistent with the supernova value, and in which the reduced chi-squared is acceptable. And in fact, it's not only acceptable, it is slightly better than the standard lambda CDM, best fit reduced chi-squared. although I don't know if that's statistically significant. So that is what we said. So in 2018, we said, here are some toy models, and we can get them to work and explain the Hubble tension in this way. Now, since then, there have been tons of papers written that have reproduced our results, tried, doing the same analysis with different data sets, different assumptions, etc. I'm not going to summarize all of those except for a few recent ones that are interesting. Now, I should say that the scenario, the physics is designed so that the cosmic microwave background power spectrum for the temperature and also the CMB polarization, this other curve over here, and the temperature polarization, the curve down here, the parameters of the model are chosen so that they agree very well with the measurements that have been made so far. However, the measurements that have been made so far extend up to L's of a few thousand. And there's no reason why the best fit early dark energy models and the lambda CDM models should agree at higher values of L. So in fact, if you go through and take the two best fit models, early dark energy and lambda CDM, what you find is that they have different predictions for the small angular scale or high L features in the cosmic microwave background temperature polarization spectrum that are going to be measured by experiments such as these. And as it turns out, within 3 years, there was a paper that appeared by the Atacama Cosmology Telescope collaboration, a work led by Colin Hill at Columbia University, where they analyzed early dark energy models within the with new data that they had obtained on small scale CMB fluctuations. And the two things I want to tell you are, first of all, these people, these are not Vivian, this is not Tristan, this is not me, this is not Tanvi. These are independent, very circumspect and careful and unbiased and dispassionate external experimentalists looking only at the data and not their theoretical preferences. And in fact, Colin Hill had written an earlier paper where he thought that early dark energy was not consistent with galaxy surveys. But in this paper, the result is that their analysis favors early dark energy with a higher Hubble constant over lambda CDM at greater than the 99.7% confidence level. So the first thing that I need to tell you is that, this was a great opportunity for new measurements to kill the model, but the new measurements have not killed the model. The model is still alive, or not the class of models. The idea of early dark energy as a solution to the Hubble tension is still alive, even with precise new data. The second thing I need to tell you, though, is that this result should be viewed as preliminary. This is a small fraction of the total ACT collaboration data that they've obtained. What we have learned with CMB analyses in the past is that the initial analyses were trying to understand the cosmology simultaneously with the experiments and the systematic artifacts. And so I would call this preliminary. But the other thing I want to tell you is that, as I said, there's only a small this analysis was done with a small fraction of the data, and the rate at which the quality and quantity of CMB data on small scales is increasing is pretty impressive. And whatever is said here is probably already obsolete or greatly improved upon, or will be shortly. So early dark energy is consistent with tests, has undergone tests since it was proposed in 2018. It is surviving, and it will be tested even further in the future. So if the Hubble tension is real, and if early dark energy is what's going on, it's kind of interesting because it implies that in addition to the non-zero value of the cosmological constant today, and the non-zero value of the cosmological constant that we infer from evidence for inflation in the early universe, there's another cosmological constant, or something that behaves like a cosmological constant at a redshift of about 10,000. So it seems to imply recurring periods of lambda-like behavior throughout cosmic history. Such a possibility was anticipated more than 20 years ago by two different papers, Dodelson, Kathleen Henn Stewart, and Kim Greist, where they postulated a dark energy model, quintessence model, in which there was a potential with small bumps and wiggles, and that allowed you to have a dark energy density that would occasionally fluctuate up and become important dynamically, but in most other times in the history of the universe would be dynamically irrelevant. So this is the cosmological constant today. If you actually look, they actually had an early dark energy by chance around 10 to the -4. I don't think this is a prediction, but random occurrence. And one of these back here is inflation. Another possibility comes from the string axiverse, where there's several hundred axion fields that have low masses with masses that are distributed logarithmically. And then in each logarithmic period in the Hubble, each logarithm of the Hubble time, there's some chance that one of these axion fields may act like dark energy. So that's another possibility to account for recurring periods of cosmological constant-like behavior. There's also some resemblance to these assisted quintessence models, which are sort of some combination of this idea and the string axiverse idea. And there's a very nice paper by Vivian Sala and Robert Caldwell last year investigating this possibility for early dark energy. So that is what I want to tell you about early dark energy. It's a modification to early universe dynamics that solves the Hubble tension. It has survived several, a new generation of tests, but there's going to be much more precise and robust analyses coming out with new data in the future. And if it's real, it might lead us to give us some hints about the ultra high energy physics that gives rise to the cosmological constant, inflation, etc. So that was my early dark energy talk.
Can I interrupt?
Yeah.
So it should be pointed out that in addition to the high value of the Hubble constant that Reese gets, there is a lower value of 69.8 plus or minus something by Wendy Friedman using the tip of the red giant branch. And so if you, with dark energy, early dark energy, fit one, you don't fit the other. And so consequently, and then there is another problem with the high value, namely the age of the universe. As Reese has pointed out, you come out with a younger universe and younger than 13.8, and it turns out it's around 12.7. You're in tension now with the age of the oldest stars in the Milky Way galaxy. So let me now go back to the tip of the red giant branch of the result of Wendy Friedman. That also depends on the deceleration parameter. They usually don't mention that in the abstract, but in the body of the paper, you're making a power series expansion. Of course, the deceleration parameter enters. But what I found is if I took at redshift of 0.07, which is in the range of redshifts that she used, if I change the deceleration parameter from one of an accelerating universe to a decelerating universe, the value of H naught came down to within 0.1% of the CMB value. And so the question really arises, if we have this tension, which David Gross said really is a crisis, shouldn't we also consider not merely these early dark energy, but consider the possibility that we're not dealing with an accelerating universe, but a decelerating universe, or put everything on the table, not just some assumptions. And what I'd like to suggest is that, at least with respect to the tip of the red giant branch measured by Wendy Friedman, it looks, if they were to redetermine their value with a decelerating value for the deceleration parameter, they would find something so close to the present value of 67.4 that the CMB gets that the tension would go away. And then the problem would be, with, of course, with the Reese's value using the separate variables. But as I say, you've got then tension with the age of the oldest stars in the galaxy. Well, I just thought I'd mention this. Perhaps you might want to comment.
Yeah, I'll comment briefly. So the measurements are tricky, complicated. There are a lot of steps that go into all the analyses. I am not expert on all of them, and there isn't enough time to go through all of them. So there are some discussions about the tip of the red giant branch calibration that they're using to get to the 69.8. And there are other people who've done, analyze the same data with different calibrations and find that the tip of the red giant branch value is consistent with the supernova, the earlier supernovae value. About the age of the universe, I have a slide that I was going to show you and then I took out in the view of time that actually shows that there is consistency between the ages and the omega matter and the Hubble constant. But it is true that the age measurements, which for many years were plagued by very difficult systematic effects, have gotten a lot better over the years and will get better with time. And those will become interesting constraints, but at the time, I think everything is consistent. Now, about the getting rid of the cosmic acceleration, I don't think you can do that. So for the reasons I explained, if you want to resolve the Cepheid variable values of H naught with the CMB, it requires that you have some type of dark energy that violates the null energy condition. So I don't think we're going to rule out, or I don't think we're going to go back to decelerating universe. It's just I don't think it's feasible. Okay, well, we can talk more afterwards if you want. I have lots more to say.
Sure.
Okay. Well, I got until 4:15. I'm gonna get COVID shut. Until then, yeah, or get up another time. So I want to tell you about some more recent work on the cosmic optical background excess, which I don't know if you've heard of it or not. It's something that's very interesting, but hasn't got a whole lot of attention. So astronomers or cosmologists like to measure the extragalactic background light density. So roughly speaking, this is the energy density in photons as a function of the photon wavelength. And they've been working really hard to measure it as a function of frequency over many orders of magnitude. Most recently, there was a measurement that was done by Marc Postman, who's a scientist at the Space Telescope Science Institute, his collaborator Todd Lauer, who I think is in Arizona. They've been working together a long time, and the New Horizons team. So you all remember New Horizons? That was the NASA mission that was launched 15 years ago, 16 years ago, and 3 or 4 years ago, I can't remember exactly. Did a flyby past Pluto and Charon and gave us those beautiful pictures of Pluto. Well, that spacecraft was sent out past Pluto. It took those pictures and it's still going. And I don't know if you remember, but about 2 years later, it took a picture of a Kuiper Belt object. This thing looked like a peanut. But this telescope is still out there. It has a camera that takes pictures at optical wavelengths. It collects light at optical wavelengths. It's still functioning and they're still in contact with the instrument. It's now greater than 50 astronomical units from the sun. And Marc Postman and Todd Lauer got in touch with the New Horizons team and they convinced them to point the telescope in some random empty point in this region in the sky. And they just stared and they measured the intensity of the sky, the brightness of the sky at a wavelength of approximately 0.6 microns. I think strictly speaking, it's a broad band that goes from about 0.4 to 0.9. And it's significant because no one has ever been able to measure the brightness of the sky at these frequencies before because of zodiacal light from the sun. So even the Hubble Space Telescope, it's above the Earth's atmosphere, but it's still pretty close to the sun. And there's a lot of zodiacal light at these wavelengths that makes it impossible to actually figure out the brightness of the sky. So they were able to, for the first time, measure a non-zero sky brightness at these wavelengths. It's an 8 sigma detection. These people also are very deeply involved with Hubble Deep Field galaxy number counts and luminosity function measurements. And what they find is that the sky is about twice as bright as you would expect from all of the integrated light from all the galaxies that we know about from Hubble deep counts. So this is the cosmic optical background excess or anomaly. This analysis was recently redone by a graduate student at Rensselaer Polytechnic Institute, I believe, and confirmed. There is initial data from the James Webb Space Telescope that suggests that some of the models that they used are fine. And so this is the cosmic optical background excess or anomaly. It seems like there's 2 photons in the sky from every photon that we would expect from the galaxies that we know about. So an obvious, explanation or hypothesis, which is not at all profound, is that maybe this is a decay line associated with axions. So this is not so profound as to warrant a paper, but we wrote a paper about this for another reason, which I'll get to in a few slides. So axions are believed for a variety of reasons to exist, or axion-like particles. The parameter space for such models spans a broad range in axion mass and coupling constant. And then there's constraints from all over the place. If we were to ascribe this cosmic optical background excess to axion 2 photon decay, it would fall somewhere in this range of the parameter space. And so we postulated, that what if axion-like particles or axion decays are contributing to this cosmic background excess? And it's a straightforward analysis. There's some complications that you'll see in some of the next slides, but the analysis is very straightforward and no need to pay too much attention to the details. I did want to blow up the constraints in this regime over here, this wavelength regime around EV. So there are bounds from MUSE and VMOS. These are direct searches for axion decay lines from galaxy clusters that have been observed with the VLT. So they looked for axion decay lines, they didn't find them. That rules out these regions of the parameter space. The cosmic background excess can be accounted for by this darkish strip in the parameter space. And some of it is ruled out by these null search, direct telescope searches, but there's more that's still possibly available. And then there is this gamma ray curve, which I'd like to explain, which is also interesting. And then there's this line intensity mapping curve, which is also interesting. And that was the subject of the first paper we wrote, and this gamma rays are the subject of the second paper. So if you have optical photons in the universe and a high energy photon of gamma rays propagating through this cosmic optical background, if the gamma ray energy is high enough so that the center of mass of the 2 photons is greater than the rest mass energy of the electron-positron pair, you can pair produce electrons and positrons and thus attenuate the propagation of gamma rays through the universe. So you can calculate the optical depth for a photon of energy E coming from a source redshift Z to be absorbed, and it's some integral over the path length of the photon energy density. So we did a little analysis using Fermi data. So Fermi has actually measured the optical depth to gamma ray absorption for sources redshift Z sub S. Where's my slide? They've done this with about 800 blazars at redshifts up to a few. And what we did is we took their measurements of these taus. Let me see. So we took their measurements of tau, and then we tried to model, calculate the expected value of tau as a function of gamma ray energy and source redshift. Taking into account, where is it? here it is, taking into account the known contribution to the optical background from galaxies of redshift less than 6. What we infer about the contribution of the optical background from galaxies greater than 6. So this involves some theoretical modeling calibrated to high redshift galaxy information. And in addition, and then what we did is we tried to see whether the optical depth that we infer from the known astrophysical sources agrees with what Fermi saw. To make a long story short, here's the long story. So these are different, sources at different redshifts, and the inferred values of the chi-squared for the fit to tau and the model parameters. To make a long story short, for some sample of the gamma ray blazars, we actually obtained some 2 sigma-ish hint of a non-zero detection of an excess of an excess of optical photons beyond those expected from the cluster, the galaxies that we know about. We're not making too much of this because it seems like the data is weighted quite strongly by a handful of strange blazar spectra. If we remove some of those strange blazar spectra, we get a different constraint, which is actually more constraining. But again, there are issues in the data that we don't understand, so we're not, claiming this as a detection, although it seems to be an interesting hint. But if we are actually very conservative, we actually don't find any evidence, robust evidence for an optical background excess from the gamma rays. We actually find an upper limit. It is the most constraining upper limit over some regions of the parameter space. But I do want to say there's still some overlap between the allowed regions and the cosmic background excess hinted by New Horizons. And it also overlaps with the hints that we got, albeit with some details that we don't fully understand. So there is consistency between the cosmic gamma ray background attenuation measurements and the optical background excess detected by New Horizons. So there's a possibility that it could be axions, but we're not absolutely certain. So in either way, though, we have very strong space-dance axion photon coupling over this range of axion masses. But I did want to tell you one more thing that I think is interesting. So here is the region of the parameter space, axion parameter space that would be needed to explain the New Horizons excess. And it turns out that if you want to test this hypothesis of a cosmic background excess with statistical significance, all you need to do is wait a few years until the launch of a NASA mission called SPHEREX that is going to do something called line intensity mapping. So line intensity mapping is a new way to study large-scale structure. Instead of measuring the distribution of mass on large scales by measuring the positions of billions of galaxies, we actually use telescopes with poor angular resolution and simply determine how bright is this region of the sky versus this region of the sky. We moreover do it using an identifiable spectral line, and we do make the measurements of different redshifts, different frequencies. So we actually can obtain from line intensity mapping a 3-dimensional map of the luminosity density of the emitters. Here's a list of some of the lines that people are considering or now measuring. There's an experiment called COMAP that is making these CO measurements as we speak. There's a project called TIME that is attempting to get this C2 emission line. And then there is this mission called SPHEREX, which is a NASA mission that's about to launch, that is going to detect some of these optical UV lines associated with the hydrogen Balmer and Lyman alpha trend. Balmer and Lyman series transitions. Here's sort of a cartoonish, semi-cartoonish picture of what a line intensity mapping experiment looks like. This is a map of what a galaxy survey would look like at redshift 5 if you could actually measure redshift and observe galaxies at redshift 5 and detect them all. Here is what it looks like with a realistic, telescope survey of redshift 5 galaxies, where you can include only the galaxies that you actually detect. Here is what an intensity mapping experiment would look like if you use the CO lowest rotational transition carbon monoxide. You wind up with the mass of the intensity of the mass distribution look like this. And the same thing measure with 317 gigahertz transition of C2 will give you a more higher resolution map that looks like this. And both of these can be done with fairly simple, relatively small telescopes and fairly modest telescope time. Intensity mapping is interesting because a lot of the lines that we're focusing on trace structure at redshifts, 3, 4, 5, 6 up to 10. Which tend to be larger than the redshifts probed by galaxy surveys. Here's sort of a snapshot of the experimental parameter space. Each one of these is the name of a given project. It scans large-scale structure at a given redshift over some angular size on the sky, some fraction of the sky. I do want to mention that there have been investigations about how effective line intensity mapping could be used in terms of determining neutrino properties. So it was investigated in this paper by Disga et al. Last year, how the combination of line intensity mapping, the blue, with Planck, the gray, could be used to constrain neutrino masses, the overall neutrino mass scale m sub mu. So you see that intensity mapping offers the prospect to provide very useful information. The other thing is you can also use line intensity mapping to look for other aspects of new physics, and in particular dark matter decay, for example, axion decay to 2 lines, and also neutrino decays. So an axion decays to 2 photons. Beyond the standard model physics, if we go beyond the standard model, you can have a heavier neutrino mass eigenstate decay to a lighter neutrino mass eigenstate through a transition magnetic moment that is mediated not by the standard model W, but perhaps by some new supersymmetric particle, and have it decay on a time scale relevant for cosmological observations. So if you have a neutrino decay line or an axion or other dark matter decay line, that decay line will show up in a line intensity mapping experiment as an unidentified line in the survey. So the idea is that you might see with the line intensity mapping experiment some unidentified line. And if you then want to figure out whether it's actually associated with dark matter neutrino decay, you would want it to be distributed in the same way as large scale structure. So you could test that hypothesis by cross-correlating with large-scale structure. You can also test that hypothesis by making sure that by checking the redshift at which the line is appearing. So we measure a line at some frequency, but we don't know what the redshift is. But if we can measure the clustering, which we do with line intensity mapping of that line, the anisotropy in the clustering along the line of sight and transverse to the line of sight allows you to infer some information about the redshift. There is also something called the voxel intensity distribution, or VID, which is the 1-point probability distribution function of the luminosity density of each pixel. This is what the voxel intensity distribution looks like in a standard cosmological model. And if you have a dark matter decay line, that is going to give you a boost at the higher intensity part of this voxel intensity distribution. And we studied the parameter space, and I will tell you the 2 interesting conclusions. So first of all, we explored the possibility to constrain or probe the parameter space for neutrinos that decay by magnetic moment transition. And this is the frequency of the transition. This is the sum of the neutrino masses. So this is related to the mass splitting. And this is the inverted hierarchy, the normal hierarchy. This is the prediction for the frequency versus the sum of neutrino masses. And these are various intensity mapping projects that are going to be pursued. COMAP is happening now. CCAP prime is under construction. That last is sort of like a next generation. So this should not necessarily be very compelling for the first generation, but will become constraining in the next generation. And then there is the thing that I started with, the cosmic optical background excess. So if you want to postulate that the cosmic optical background excess is due to an axion that is undergoing two-body decay, such an explanation is in fact consistent with all constraints. It is also consistent with hints of a cosmic background, cosmic optical background excess from gamma ray attenuation measurements. But what we show here is that with SphereX, this is our forecast for what SphereX should be able to do with line intensity mapping in terms of the constraint. And we have two plots, two figures, two lines here. This is sort of a very optimistic estimate that depends on our ability to deal with zodiacal light. And this is a less optimistic estimate, assuming that we have to model out zodiacal light contributions. But what you see is, regardless, this cosmic optical background excess, you might look at it and say, well, they didn't know what they're doing. There's some unaccounted for background. I don't know, I'm not sure if it's due to axion decays, but if you're willing to entertain the possibility that we are looking at a line decay of a dark matter particle, that hypothesis is going to be verified or disproven with high statistical significance in a few years when SphereX launches and starts to take care of it. So I think I forgot to put in a conclusion slide, but that is what I have to tell you. So number one, early dark energy is a possible class of models to account for the Hubble tension. Some would say there are best models for accounting for the Hubble tension. Other people have said that they are the least unappealing models to account for the Hubble tension, but they're there, the Hubble tension, And there's this new cosmic background excess that has been detected by the New Horizons telescope, which is the, allows for the first time an actual measurement of the brightness of the sky, simply because it's so far from the sun that we don't have to worry about scattered light from the sun. And again, there are uncertainties in the astrophysical contributions, but again, very knowledgeable and qualified people have looked at this, and there's no obvious astrophysical solution that comes to mind, and there's no obvious solution that's come out of the early release JWST measurements. So you can postulate you can postulate an axion for some other decay line, which is not so profound, but what's interesting is that line intensity mapping is this new cosmological tool that we're going to have in the next few years that will allow us to test these hypotheses. And finally, there's this gamma ray attenuation. There's a huge amount of data from Fermi. It's very, very good data, information about attenuation of high energy gamma rays from sources at TeV sources at redshift of several. And that can also be used to probe the cosmic optical background excess. And we find that, information from Fermi telescope is consistent with New Horizons. So I'm pleased to take questions.
Yeah. Okay. Thanks, Mark, for this excellent talk. So, so people can ask their question by raising their hand. I can see one hand from George. So, George, please unmute yourself.
Thanks, Mark. That was a wonderful talk. Really amazing. So just an issue with early dark energy. There were other crazy schemes to come up with something kind of like early dark energy. But there's an issue maybe in getting rid of it. and how it goes away. So there are a lot of crazy schemes, including, unfortunately, ones by me and Amol Patwardhan, who's not on the call here, I think. But looking at some kind of a late phase transition, where late means post recombination, but not to post recombination, where the dark energy, there's a phase transition in the vacuum, and you sweep up the dark energy, the early dark energy, onto bubble walls. The bubbles coalesce, the walls collide, and that energy on the bubble walls is dissipated as radiation. And so the problem with these is that you're kind of caught between a rock and a hard place, in that you kind of, to explain the Hubble tension, you have to go to later and later phase transitions, of order redshifts of a few hundred. But that means it's harder to redshift away the radiation. And of course, you have no idea what the radiation, if you can do this, how that radiation will be dissipated. But I'm just wondering if you just in my mind, I'm connecting the first part of your talk with the last part, in that those, if nothing else, those are the optical background is a constraint on schemes like that. Any thoughts?
Yeah, that's an interesting idea. I have not thought about that. I haven't looked at these models, the phase transition models, carefully. First question I'd ask is about the baryon acoustic oscillation constraint.
These are on much smaller scales. So the enclosed mass scale for the nucleation scale would be, I don't know, like 10 to the 8 solar masses, something like that.
Right, but if you leave the sound horizon unchanged, you're still inferring a Hubble constant of 68 from the baryon acoustic oscillation peak. But as far as the radiation, yeah, I haven't thought about that. Sounds interesting.
Thanks, Mark.
Kyle, can you please unmute yourself?
Hi, that was a great talk. Thank you, Mark. On one of your slides where you describe the potential for this new field, it's like 1 minus cosine to the n. That was with the first half of your presentation.
Yeah. Go ahead. I'll be there in a second.
Okay.
Oh.
I had to make sure. Okay, yeah. So as one of your plots in the corner plot was the limit as n goes to infinity.
Yeah.
So for that case, the potential is just like a repeated square well.
Yeah.
Infinite square well. So does the initial value for the fields phi have any, like, does it not matter?
In the limit, yeah, strictly speaking, the limit that n is equal to infinity, there is no such thing as an initial field value.
Okay.
There's details in the calculation that I didn't go through, but this n equals infinity, these n equals infinity curves do not actually solve the equations for the oscillations numerically. We use a generalized dark matter description. Essentially effective description, which has been calibrated, so we're confident in the results. But you're correct, it's a
Okay. And on this plot, is it log base 10 of AC? Is that the initial value?
So A sub C is the scale factor at which the early dark energy becomes dynamical. So it's somewhere between 10, it's close to 10 redshift. This is redshift, about 6 or 7,000.
Okay, right. You said you didn't have that on the plot. Okay, yeah, never mind. Okay, thank you.
Sure.
The next question is from Brian. Brian, can you please unmute yourself?
Yeah, thanks, Mark. Just a quick thing on the noise environment, not my kids, but someone else's kids. What do you have to say about early magnetic field, primordial magnetic fields? Levon Pagosian and others have worked on this. Can you say anything about the ability to rule those out as an alternative to early dark energy, or as a solution to the Hubble tension?
I think the magnetic field models are possibly solutions, but I don't think we have enough information yet to know. What's difficult is that it's really difficult to evolve the perturbations in these models. So I don't know that I've seen a calculation that's careful enough to allow us to decide. But it's an obvious thing to try. It's a reasonable idea, an obvious thing to try.
Thanks a lot.
Are there any more questions to Mark? I don't see any. So let's thank Mark one more time for his very excellent talk. And
Thank you very much.
yeah,
Thank you, Mark.
yeah, and we will meet next week. Thank you, Mark.
Thank you, Mark. Take care.
Thanks. Good to see you.
Good to see you too.
Frank, before we go, if you do want to talk more, you can send me an email. We can try to set up a time. Or email me whatever questions or comments.
Sure.